Today I have another Pi Pico demo. We're going to be doing a standard I/O command console. Basically you can connect a serial terminal to the Pi Pico and execute commands by typing them into the command prompt. The application itself is going to be another multi-core application where one core will be used to handle the standard I/O, basically reading character input and then echoing back characters that are entered through standard I/O. Now, for the serial connection, there are two approaches that can be taken. The USB port on the Pi Pico can be used for a standard I/O serial connection, or you can use one of the UARTs. By default, UART 0 can be tied to standard I/O as well, and then use some additional hardware to connect your workstation to the UART. In this case, just for this example, have these boards that have a CP2102 chip on them. See if we can get that in focus. A simple chip that just goes from a USB connection to UART TTL. It will have transmit and receive for the UART, a ground signal, and then in this case it has also 3.3 volt out and 5 volts out. We won't actually be using those, but these are kind of handy because you want to make sure that the transmit line is actually 3.3 volts. You don't want to be using 5 volts on the UART connection on the Pi Pico, and so the chip that's on these will change the 5 volts to 3.3 volts for the signals that are going to the Pi Pico. For the demo, we'll actually demonstrate both the USB connection and the UART connection, and then we can look at a schematic here. The UART 0 by default is on pins 1 and 2. The transmit and receive are on pins 1 and 2 of the Pi Pico, and we will need to connect the transmit from the Pi Pico to the receive on our USB to UART bridge, and then the receive on the Pi Pico goes to the transmit, and then we will need a ground connection between the bridge chip and the Pi Pico. So I already have everything wired up here. You can see we have our couple of wires going from pins 1 and 2 that we'll be using UART 0 for standard I/O, and that is connected to the transmit and receive on our USB to UART bridge, and then of course we have the just standard USB connection that we will also be using. So let's go ahead and grab the code that we're going to be using. So as with the other demos, everything is on GitHub, so we can say let's go ahead and git clone yes github.com, and it is Pi Pico. We're using C, and it's a console. There we go. So we have our project now for the console. And let's take a quick look at the code. Let's bring up our editor. Okay, so console. So first let's look at the CMake list file. Just pretty standard stuff that we have, setting the version of CMake that's required, setting up our Pi Pico SDK, which is already installed on the workstation, and then defining our project. We're just going to call it console, and then the version or the standard that we're going to use for C and C++. We initialize the Pico SDK, and then here, so the console program is broken up into multiple source code files. So for the console program, we're actually going to compile main.c, console.c, and command.c. We'll take a look at all of those, and then of course the linking. Since this is going to be a multi-core program, We need the Pico multicore library along with the standard library, and then just the normal, the output from the compiler we want to be a Pico binary named console. And then these two are important. So this is what actually enables the standard I/O on the USB or UART 0 connections. We just tell it that we're going to enable standard I/O, in this case UART, on our console project, and then 1 is to enable or 0 to disable. And in this case, we're also enabling standard I/O on USB. So you can actually have them both enabled simultaneously, or you can choose one or the other. So next, let's take a look at the main source code. So we start off by including the header files for the console and command source code. Reason being that we're going to use functions out of that source code. We declare this init function that's going to be used down here. Just have to declare it before it's defined. And we're going to declare a semaphore called sem command. This is going to be used to control the execution of commands. We'll see that when we look at the source code in the command processor. And then the main code is going to run obviously on core 0. First thing it does is it runs the initialization function. In the initialization function, we set up our standard I/O, initialize, flush any data that's in there right now. And then we don't want buffering of any characters. We want them to be sent out immediately because the console is going to use basically echo out. So when you type a character on the terminal and it's sent to the console will echo that back, so it will be displayed in your terminal. And then we need to initialize the semaphore that's going to be used for the command processing. After it initializes, comes back, first thing it does, uses the multi-core launch on core 1, the console. So console is the code that's going to read input from standard I/O and then echo the characters back. We'll take a look at that. Once it launches that, then core 0 will run the command processor, and we'll take a look at that after the console. First, let's take a look. So the console source code, this is going to be running on core 1, and starts out, it defines a buffer for the command line. So this is going to be shared between the console and the command processor. It's where the actual commands will be stored before they're executed. And then here's the actual console process, the function that was called by multi-core launch core 1. So this is going to be running on core 1 on the Pi Pico. So we define a variable that we're going to use to store each character that's entered through the terminal. And this is a bit tricky. You might assume that this would be just a character, but instead it needs to be a 16-bit integer because the error codes that are returned are 16-bit. Even though for the characters that we're sending back and forth, we only care about 8-bit characters, but in order to capture error codes, this needs to be a 16-bit variable. Then we have a line buffer. It's similar to the command line buffer, but this line buffer is basically the edit buffer. As you enter characters or erase characters through the terminal, they're modified inside this buffer. And then we just have a cursor pointer so we know where the cursor is at in the line buffer. Then we run this function to initialize the console, and we're passing it just the pointers to the two buffers. So let's go take a look at this method, init console. So here we are, init console takes the two buffer pointers, and it basically is just going to clear out. This clear buffer method clears out the buffer, and then the buffer is actually one character longer than the number of characters that will be allowed, and so the final character is a null. This is just to make sure that it always has an ending for the string. So when we run string commands against this buffer, we always want to have a null character at the end of the string, so that this final character will never be overwritten. We will only go up to just the character just before this. So that's the command line's cleared, command line buffer, and then the editing line buffer is cleared as well, and same thing, null character at the end. And then we run this flush input just to make sure that before we start processing the console, we want to ensure that the input, there are no garbage characters in the standard I/O sitting there waiting for us. So let's actually take a look at these two methods before we move on. So the clear buffer method, there we go. So clear buffer, it's just past the buffer. So you can see it's just using memset and setting the contents of the buffer with null values. And then it's just returning what is the length of the buffer. And this is just for convenience. The length of the buffer is stored elsewhere, and so, well, for the cursor mainly. And so this is just a convenience thing to reset the cursor value each time the buffer is cleared. Then the other function we want to see was the flush input. So same thing, flush input, it's going to read characters. We're going to use a 16-bit variable so we can capture error codes. And then what it does is it just loops doing a timeout character read of standard I/O, just going to get one character at a time. And then if no characters there, it will time out after 500 microseconds. And it's going to run this loop as long as it receives characters and it doesn't receive either a timeout error code or a generic error code. So this is where the 16-bit variable is important, because if we used a char, a character variable, then we wouldn't get the full value of the error code. A character can only store values between 0 to 255, and the values of these errors are greater than 255. So we need a 16-bit variable in order to see these actual error codes. So if we go back, so after initialization does the flush, so initialization of console is done. And after that we get into the continuous loop. So core 1 will run this indefinitely, this loop, to process the console. First thing it does is get a character from the standard input. Some of the characters that come in, so this is a very simple console, it doesn't have any advanced editing and whatnot. So some of the characters that might come in, we just want to ignore them. And so that's all this list is of checks. These are just possible characters that might come in that we don't really want to do anything with them. So the loop will just continue. It reads the character from standard in and then just goes back and reads again. Another possibility is there might be an escape sequence. That is, there will be an escape character that comes in and it will be followed by additional characters. So if we get an escape character, then we use the flush input. So as we used before, the flush input will read characters until it comes to a timeout. So there's nothing else remaining in the standard in buffer. And so then we'll just continue on. So we're not going to do anything with the escape sequences, just read them in and just flush them out. And then the user might hit enter. So this would be the enter character. If an enter character is read in, then we want to do a memory copy. We're copying from the line buffer that we're editing on the console and copying that into the command line buffer. Then the next thing we do is we clear the line buffer. So we clear the line buffer because now we're done. We want that whatever was entered to be sent off to be processed by the command processor. So we clear the line editing buffer, and this will just set the cursor pointer back to 0. And then we need to print a new line so in the terminal the cursor will go to the next line. And then we do a sem release on the semaphore, and this is what allows the command prompt, well, just lets the command prompt know that it needs to process the command now that is in the command line buffer. And we'll see how this works when we go look at the source code for the command processor. And so then after enter, this is done, it just continues back to the top of the loop to get the next character. Other possibilities, if we get an ASCII backspace or delete key, then we want to erase a character from the line buffer, the editing buffer. If the cursor is already at 0, then there's obviously nothing to erase, and so we just continue back to the top of the loop to read the next character. However, if there are characters, then we call the delete character function, which will return the new length of the buffer and store it in the cursor. And we'll go take a look at this, how it deletes the character. After it deletes the character from the line buffer, it uses an ASCII backspace. So this is being sent to the terminal through the standard I/O. Is going to print a backspace character, and then a space character, and then another backspace. So we have to do this so that in the terminal, the character is erased on the screen. So the way it does it, when you do a backspace in the terminal, it doesn't actually remove the character in the display, it just moves the cursor in the terminal. So we have to do a backspace and then a space to erase the character, and then backspace again to get the cursor into the position we want. And then again continue on to the top of the loop to get the next character. And then the final possibility, if the cursor has reached the end of the line length, then we can't enter any more characters, so we don't want to do anything. So we'll just continue to the top of the loop. And if we make it this far, then it's just a a regular character input, letters, numbers, and so we want to append whatever character it was that the user entered into the line buffer, and then return the new cursor position. And then this is the echo out, so it's going to print that character back to the terminal. Because when you type a character in the terminal, assuming you have echo off, when you type a character in the terminal, it sends that character code to the console, to the Pi Pico, but it doesn't show that character in your terminal. So the Pi Pico has to echo that character back so that it will be displayed in your terminal. And then that's the end of the loop. So the core 1 just will continually run this loop processing character input on standard I/O, and then either echoing out, handling the enter to send the final command to the command processor, or just doing nothing for characters that we don't really care about, escape sequences and stuff like that. Before we go to the command processor, let's take a quick look at the console header file. So we've got some include statements that we need, but some of the key things is this line length. So this is what actually defines the length, the maximum length of both the line buffer and the command line. So you can only enter up to 80 characters, no more than that. It'll just stop once it reaches 80, because the buffer, this is what determines the size of the buffer. So we don't want to allow anybody to enter characters beyond that, because it'll start overriding memory, possibly for the stack or the actual code the program is running. Then we just define our methods that we're going to use in the console. And then so it's going to use an externally defined semaphore. So if you recall, we defined the semaphore sem command in the main source code, but we're using this inside of the console, right? The console, when a command is ready to be processed, it will use this semaphore. If we just go back one more time, when you hit enter, it's going to do a sem release on the semaphore to allow the command to be executed. So let's go ahead and take a look now at the command processor source code. So command processor have our includes that we need. This is just defining a constant string of characters. That's a help message, and then this is the loop that's going to be running on core 0 to process any command. So it starts an infinite loop, and the first thing it does is uses sem acquire blocking on that semaphore, and it will wait here. So this is where the command processor, when it starts, it's going to wait for the console to release this semaphore before it does anything. So that's why the console will read in the commands. When you hit enter, it saves the command in the command buffer and then releases the semaphore to allow this thread that's running on core 0 to then continue on. So when it continues on, first thing it does, check to see is there actually anything in the command line buffer. If there's nothing in there, if the length is 0, then it just continues back up, and then it will block again and wait for the next command. The first command we have here is if we do a comparison of the command line buffer to help, and it's equal, the string compare will return a 0 if they're equal. If they're equal, then it prints the help message to the console, which is this message up here. Then the next command that we have is boot ROM. So if you enter the boot ROM command, then it uses the reset USB boot. And what this does, this is similar to resetting the Pi Pico and holding down the boot select button. It causes the Pi Pico to boot into the boot ROM so that you can copy firmware over the USB connection using mass storage. And we'll actually demonstrate this. And then the last thing is to just print an error message that whatever the command is that you entered, it doesn't know what it is. These just invalid commands. So let's go ahead and build this. So let's create a build folder. Going to build. Oh, and we need to make sure, so it's going to need our environment variable for the Pico SDK location. So Pico SDK path is equal to home directory, it's in embedded, and then Pico SDK. So that's the path to our Pico SDK. Now we can do cmake dot to use the cmake file to create our make file. There we go. Now we say make. This will compile the SDK files we need and our source code for the main console and the command processor, and link everything together. And there we go. So let me reset the Pi Pico into boot mode. Okay, and now it should be mounted, and there's our Pi Pico. So all we have to do is copy our console UF2 file to the Pi Pico mass storage. Okay, so it's copied over, it's running. So now to actually connect to serial console. Well, let's look at this real quick. So we enabled both the UART and USB standard I/O. And so if we look at our TTY devices, we will see that there are two for the Pi Pico. This one is the USB serial connection, and then this is our USB to UART bridge. Since the actually, let's go ahead and show this. So the USB UART bridge, it's always connected. This will always show up whether the Pi Pico is running or not, because it's plugged in and powered by the USB connection to the workstation. The TTY ACM0 is the USB port on the Pi Pico itself, and that TTY will only show up when the Pi Pico boots and runs your code and initializes the standard I/O. When it goes into mass storage, this device will disappear. Let me bring this back. Terminal. The TTY ACM0, this will not be available when you're in the mass storage mode. So if you did a reset and boot select to come up into the boot ROM mode to copy over your binary files, your code to the Pi Pico, that device will disappear. Actually, let's go ahead and do that. So we boot up, and right now we should have the mass storage, and there it is. So the mass storage device is there, so we can copy firmware over. But that means that the TTY ACM0 is gone. So that device only exists when it's running your code and you initialize the USB port on the Pi Pico for standard I/O. Whereas, again, just kind of repeating here, but the USB to UART bridge is always there because it's plugged in. So you will always see, no matter what mode the Pi Pico is in, you will always see your USB device for the UART to USB to UART bridge. Okay, so now that we've got those, well, actually, let's reset the Pi Pico because we want to run both. So we should have both devices, TTY devices. Okay, there we go. So we have both because they're both initialized. That's the USB port. That's the USB to UART port. So let's go ahead and so I'm using Screen. You can use other programs for your serial terminal, Minicom, PuTTY, whatever works. I use Screen. So if we connect to the USB, TTY USB, and we want 115,200 baud rate. So should be, so we're getting our echo back. So if I say help, and there it echoes out the help. If I just hit enter, it'll be an empty command prompt, so it doesn't do anything. If I enter something that doesn't make any sense, it's going to give me an error message. And then of course if I say boot ROM, is going to reset the Pi Pico, and it's going to come back up in the boot ROM mode where we can copy firmware to the device. And here, just to show this in this second terminal, if we look in run media, we can see right now there's no mount point for the mass storage device. But if we reboot with the boot ROM command, and now we look, and there it is. So didn't have to press any buttons or anything. Just by using the command console, we can bring the Pi Pico up in the boot select mode so that we can copy firmware over. So let's go ahead and reset this back. I just want to demonstrate a couple more things. So this should be back. So we're back connected, running our firmware. But we can also, well, here, ls device TTY. So we've got both our devices back. We've got our, so we're using this USB 0 device up here in this terminal. But we also have the Pi Pico's USB device on this TTY. So we can theoretically connect to both of them at the same time. So just going to run two terminals. So we've got this terminal up here that's connected to TTY USB 0. We're going to run a second one down here on TTY ACM 0. So they look the same, but they're connected to different serial ports. And since they're the same standard I/O, you can see if I type in one, it shows up in the other. And the help message that shows up in one will show up in the other as well. So because they're both the same standard I/O. So it's standard I/O. One of them is coming over the USB port, and the other one is, well, the same standard I/O is also. Oops, let me take this terminal down for a moment. The other one is coming over the USB to UART bridge, but it's the same standard I/O. So we have two terminal connections, one to each piece of hardware, one to the USB to UART bridge, and one to the USB port on the Pi Pico simultaneously, but they're the same standard I/O. One or the other. Okay, so what next? Let's do just a quick demonstration of just adding an additional command. Let's go ahead and disconnect. Which one was that one? That was USB. Let's disconnect this one here as well. Oop. F4, yes. So let's go ahead and in our editor, in our command processor, let's go ahead and add a new command. Let's show microsecond time since start. Else if 0 means a match, string compare the command line, and if somebody enters time, the command time, we want to do, let's see, what is the function to get time? I want time microseconds 32-bit. Actually, let's do this. Printf, we're just going to show it on the screen. Let's say time, and it's a number, new line. There we go. Okay, so if the command is time, then I'm going to printf to the terminal time, and then a number. The number will be the number of microseconds, 32-bit number of microseconds since the Pi Pico started. So let's go ahead and do a make. Okay, and I need to just show this. Let's see what I'm doing. So I need to boot. Well, actually, let's not use the button. Instead of using the button, we already know that we have that boot ROM command. So if we go to the TTY USB, okay, so we're connected. So we can use boot ROM. Well, actually, just show it. So right now, time, it doesn't know what that is. So boot ROM. Okay, we're rebooted. So we should now have media. There it is. Let's copy our new firmware over. Oops. There we go. Okay, should be started up, and now don't have to do anything in this terminal. It's already connected to the USB to UART bridge, and I could just say time now, and it doesn't work. So it helps if you save your code after you modify it. So save, let's build again, and let's go back to boot ROM. Okay, we're connected with mass storage. Now we can copy our firmware to the Pi. Okay, now let's try time. And there it is. So we now have a new command that would tell us the number of microseconds since the Pi Pico was reset. So that's about it. The only thing that maybe is of note, I mean, you might be wondering why would you want to use you might be wondering why would you want to use the extra hardware, USB to UART bridge for your console. And it's mainly for convenience, because if you're using the USB port on the Pi Pico, the TTY ACM0 for your command console, then you can run into some issues when you reboot into the boot select mode to copy over your firmware, because this USB port has to switch from being a serial console into being a mass storage device so that you can copy your firmware over. And if you already have an application running that has control of the serial port, and then you reset the Pi Pico to come up into boot select mode, then you can get some odd things happening, and it might not mount the mass storage, so you won't be able to copy over files. So if you're using the separate UART, USB to UART bridge, then you can just maintain your serial terminal connected to the USB to UART bridge, and you can reset the Pi Pico and upload new firmware and it has no effect on this USB connection. The only thing I will say you need to be careful of with the USB to UART connection is you need to make sure that the hardware that you use is providing 3.3 volts on the receive and transmit line, that it will operate with 3.3 volts. Because the Pi Pico, it needs to be 3.3 volts. If you use 5 volts, there's the potential to damage the Pi Pico. So you need to be careful in your selection of USB to TTL UART device that you choose. Some of them might use 5 volts for their TTL data lines, and you want to avoid that. You want to make sure you're using 3.3 volts on the Pi Pico. So as usual, all of this will be, there will be a link to the GitHub project in the description of the video.